In this video, we look at the average rate of change and the instantaneous rate of change. That is, the ARC and the IRC. Our goal is to precisely describe the slope of a function at a point. We build up to that by first developing the ARC, and then from the ARC, we develop the IRC. Suppose you have a function y equals f of x, and we have 2 points, point P and the point Q. The point P has coordinates x, f of x, and the point Q, a little further, say to the right, has coordinates x plus h and f of x plus h. What is the slope of the line connecting these 2 points? The slope of a line connecting points P and Q is the difference of the y values divided by the difference of the x values. That is, this formula, f of x plus h minus f of x. On the top and the numerator is a change in y, and the bottom x plus h minus x is a change in x. We can simplify the denominator and so write the slope in this way. Again, change of y over change in x. Phrased in slightly different notation, the ARC of a function describes how it changes across an interval from one x value to another. We compute the change in the function value, change in y, which is the same as f of x2 minus f of x1, and then we divide it by the change in x, delta x, which is x2 minus x1. Again, we'll repeat this many times. The ARC is simply the slope of a certain line. What is the ARC? It's the slope of a line. It's the slope of the line connecting the points P and Q, and we'll call that line a secant line because it goes through 2 points on the curve. Here's a picture. My curve is here in blue, and I have the points P and Q, and I have this line segment connecting them. This is part of a secant line. We have the secant line going from P to Q. What is the ARC? The slope of this line in red. So the ARC is the average rate of change, delta y over delta x. There's other notation. I can use it in function notation. Again, we're summarizing here. The ARC is slope. It's the slope of a secant line. The ARC is unsatisfactory. It is an estimate for the instantaneous rate of change for the IRC of a function at a point, and we're really after the IRC. The IRC of a function is the slope of the tangent line at that point. The IRC will usually may just go through 1 point on the curve. We are really interested in the IRC, that's the slope of the function, not the ARC. But we only know 1 point on the function when we do the IRC, so we cannot directly compute the slope of the tangent line because we don't have 2 points. Instead, we will view the tangent line as a limit of secant lines as the point Q gets close to the point P. Again, here's the picture. The point P is where we would like to find the slope. And we think of the tangent line at P, drawn in purple, as a limit of secant lines as points Q, Q1, Q2, Q3 move closer and closer to P. And the secant lines are drawn in red. This means that we can estimate the IRC by computing the ARC, where the second point Q is very close to P. We can make this precise by introducing the idea of limits in the next main lecture. Before we move on to limits, let's do some examples. Here's an example. Consider the square root function, f of x equals square root of x, and let's find the secant line between 2 points a f of a and a plus h f of a plus h, where a is 9 and h is 0.5, or a is 9 and h is 0.005, and so on. We'll try out 4 little sub-examples. And then, once we've done that, use these answers to guess the slope of the tangent line to the square root function at the point 9, 3. Find the slope of the secant line between 2 points 9, 3 and 9.5 square root of 9.5. This is the first problem from the examples before, and the solution is a slope problem. Here we have to get out a calculator, but 1 point is 9, 3, and the other one is 9.5, 3.082207. That's my best approximation for the square root of 9.5. So if I have 2 points, 9.5, 3.82207, and 9.3, here's the slope. We can do that again if my points are slightly different. 9.3 and 9.05, comma, whatever is the square root of 9.05. Once again, slope is change in y over change in x, and we get this. Slope is change in y over change in x. Slope is change in y over change in x. All of these computations are the average rate of change. We have other ways of saying this. In this last problem, for example, we found the ARC as x moved from 9 to 9.002. The ARC of f of x on this interval is then the 0.16657. Let's use the answer to the previous problem to guess the slope of the tangent line at the point 93. Again, recall that the ARC guides us to the IRC. We did 4 little ARC problems, and we kept getting answers closer and closer to 0.1666 repeating. So we might guess that the slope of the tangent line at 9,3 is 1.6 repeating, which is 1/6. Our ARC values close to 1/6 suggests that the IRC is 1/6. We got 4 average rate of change values that were close to 1/6, so we're going to guess or say that the IRC is probably 1/6. Notation. We will sometimes express the ARC as occurring across an interval. We go from one x value to another. In the above problem in part A, we had 2 x values, 9 and 9.5. So we computed the ARC across the interval 9, 9.5. You'll see this notation on your homework. In the next presentation, we explore the ARC concept using the physical concepts of distance and velocity.